Alternating current takes many forms, but the square wave is fundamental in digital electronics and power switching. Unlike a smooth sine wave, it jumps instantaneously between positive and negative maximum values, creating a distinct pulse pattern over time. If we look at a full cycle of a symmetrical square wave, the positive and negative halves cancel each other out, resulting in a mathematical average of 0. To find a meaningful value, we often focus on the half-cycle average. To analyze this wave, we define the periods t. The current stays at a constant positive peak for the first half of the cycle and then drops to an equal negative peak for the second half before repeating the process. The average value of any periodic function is defined as the total area under the curve for one period divided by the length of that period. For AC signals, we specifically calculate this over the positive half cycle. By focusing on the half cycle from 0 to t2, we can determine the effective average current delivered during the pulse. This prevents the positive and negative values from cancelling each other out during our calculation. Since the square wave is constant during this interval, the area is simply the area of a rectangle. We multiply the constant peak current, Im, by the duration of the half period, which is t divided by 2. The result is elegant and simple. For a square wave, the average value over a half cycle is exactly equal to its peak value. This is a unique property compared to sine waves, where the average is lower than the peak. In a sine wave, the current spends very little time at its peak, leading to a lower average. However, a square wave stays at its maximum value for the entire duration of the pulse, maximizing the average current. Let's look at a practical example. If you have a square wave alternating between 10 amps and minus 10 amps, the average value for the positive half cycle is simply 10 amps. No complex integration is required. If the wave is not a perfect 50/50th square wave, we introduce the duty cycle. The average value then becomes the peak current multiplied by the percentage of time the signal is on or positive. When a square wave is passed through a full wave rectifier, the negative half is flipped. In this case, the average value over the entire period remains equal to the peak value, Im, because the current never drops below peak. The average value is important for applications like battery charging or electrolytic processes where the total charge transferred over time matters more than the instantaneous fluctuations of the waveform. To summarize, the symmetrical square wave has a net average of 0 over a full cycle, but its half-cycle average is equal to its peak. This is because the area is perfectly rectangular, filling the entire period interval. Let's test your understanding. If a square wave has a peak-to-peak value of 40 volts, what is the average value of its positive half-cycle? Think about the relationship between peak-to-peak and peak values. The answer is 20 volts. Since the peak-to-peak is 40 V, the peak value from 0 is 20 V. Because it is a square wave, the average value for that half-cycle is identical to the peak value. Understanding the average values of different waveforms is crucial for electrical engineering and circuit design. You now know why the square wave is the most efficient at maintaining its peak average. Generated by Vision Solve AI.